Let's give this a start. Thank you very much, everyone, for joining us. Today, I am joined with Anshul and Mark from Nvidia, and we're going to be talking about building performant AI applications with NIMs and Haystack. So before further ado, I'll just quickly introduce myself. My name is Twana, and I work at DeepSet. I'm in the developer relations team there. So that means I fully focus on our open source framework, AI framework Haystack, and that's also going to be the framework that I show you today. And we're going to build both an indexing and a RAG pipeline using Haystack and Nvidia NIMs. And yeah, Mark and Shul, would you guys like to introduce yourselves?
Hi everyone, my name is Mark Moyer. I'm a senior solutions architect at Nvidia. I work on Inference. I work with retail customers in the US. So happy to join you today.
Hi everyone, I'm Anshul, based in Munich. I'm a senior solution architect for the cloud services in Nvidia, focusing mostly infra, Kubernetes. Yeah, and happy to be part of this webinar.
All right, thank you very much. And let's start off with a quick agenda of what we're going to be discussing today. So we're going to have an introduction to inferencing, and Mark is going to take us through that. And then we're going to also have an introduction to NIMs, again with Mark, and we're going to be discussing LLM NIMs, embedding NIMs, and also possibly re-ranking NIMs. And then we're going to hand over back to myself, and we're going to start building RAG with NIMs and Haystack. Finally, and this is getting increasingly more advanced, we're going to look at how we deploy and scale NIMs with Anshul. At the end, we're going to have some time for Q&A, and we're going to ask you to please use the Q&A functionality, and we'll answer your questions along the way, and anything that's left we'll also answer live at the end as well. Before I hand over to Mark, a few FAQ answers. All of the code examples that you'll see both myself and Anshul share at the end as well are all available on GitHub. Maybe Vladimir, you can help by sharing the URL to that GitHub repository already, but this QR code will take you there as well. And just so that you're aware, all of this is recorded and it's going to be put up on our YouTube channel, on the Haystack AI YouTube channel. So you can watch this later, or if anyone wasn't able to make it, you can send that over to them. We will be sharing it hopefully tomorrow. And with that, I think we'll disappear for now and let the stage be Mark's. All right.
Hopefully you all can see my screen on your side.
Yeah.
Perfect. All right. Good morning once again, everyone. And so as you think about this presentation, I kind of want to walk you through intuition. And after walking you through some intuition, we're going to focus on trying to land that plane on NIMs. So first, just to get started, please go to build.nvidia.com. I want you to get the 1,000 free inference requests that you can use to test all the different models. And I think if you are putting any of these models into production, this is the place where you get to see sort of how fast models can be from NVIDIA. In addition, I like to mention it to people so that they go use it as a benchmarking platform for you to figure out which of these models will work for your use case. And it's a good proxy to actually see how a model works without, let's say, fine-tuning and things like that. So we're going to focus on the LLM inference sort of end-to-end pipeline and what those fundamentals really mean. And the main thing is, as you kind of go through and read different types of literature, read different documentation, you'll see technical terms. So it's good for you to have that intuition once you come in. So from an understanding LLM inference standpoint, let's start with a end-to-end super simple example. So I'm saying, hey, write me a presentation on LLM inference optimization. So I give my job at NVIDIA and I'm saying, make me sound smart. So when I ask the LLM that, I'm actually putting that entire prompt on the GPU. That's why I put it, give me 1 second, do this. That's why I put it in the middle. So thinking that, hey, this thing is now stored on the GPU. So ignore this piece. And then focus on the right-hand side. I'm generating these tokens one at a time. LLM inference is hard. So I'm denoting that with these timestamps, time 1 through time 4. And every single time a token is generated, I put that back onto the GPU. So all of these tokens that you generate are cached on the GPU. So the longer both your input and your output, the more memory you're essentially occupying on the GPU. This is why when you look at an LLM provider, you pay for your input and sort of your corresponding output as well. Sorry about that. So that's something to keep in mind in terms of what that flow will look like. And we're going to actually sort of walk through all the way to this thing called a KV cache, which is essentially your LLM's memory. In terms of high-level pieces that are happening or processes, so when a prompt comes in, I have to convert that prompt into something that the model understands. I'll show you the technical definitions after. Once we get onto the GPU, it's important for you to always have in your mind what's occupying my GPU memory, because ultimately that's the thing that you're going to end up paying for across your entire deployment. In addition, that's the thing you'll try to optimize as well. So once the prompt comes in, I'm initially going to process it. Think of it as someone asking you a question, and the longer the question, you have to wait to digest the question and then try to respond. So that's essentially what's happening on the GPU itself. We compute some attention mechanisms and all those things, and then I start generating tokens one at a time. Before an output is shown to a human, this could be either streaming or the entire output is given back to you as sort of like a lump sum. You would have to convert those tokens back to human readable words. And I encourage you to sort of abstract this for different domains. So if you're doing, let's say, chemistry, I'll have to go from some tokens back to some chemical model. So the same paradigm can kind of work across those different types of use cases. So coming in from the left, we're going to do tokenization. So this is the exact same slide as I showed before. I'm just showing you the technical terms. Prefill, there's tons of research that's happening in this space. How do you get more efficient attention mechanisms? So you'll see things like flash attention 3. There's things like optimizing with FP8, building engines. A lot of those things are happening on this side. And then once we get to decode and generation, I want you to make sure you remember this thing is generating tokens one at a time. So no matter how fast you see things being generated, it's always generated one token at a time. And at any point in time during an LLM system's sort of lifespan, right, you're going to have requests, people sending in a new request and people generating tokens during their request. So it's always good for you to understand, all right, when a new request comes in, that's a new processing block that's going to happen. And in that processing block, when I'm processing your new prompt, I'm also generating tokens for other users as well. So there's lots of optimizations to make sure that that actually happens quite fast. This next one, I want you to understand visually what is the actual data that an LLM sees. So I have text data in this case that's going to come in, but how does it get transformed for an LLM to actually use it and compute the attention mechanism? The proxy I want you to keep in your mind is that a token is approximately 4 characters. An LLM's token in its vocabulary is not a human word typically. Sometimes they are, depending on the word and that frequency in your domain data set. So in this case, I'm showing 2 arrays, and I'm showing tokens T1 through T capital V and the corresponding numeric index. So just think of this as some lookup table. And my job is to convert your input text/prompt into some vector of token IDs. So in this case, you'll see this thing. I'm saying, okay, make me sound smart. When I tokenize that, I get this vector of token IDs. And these IDs are specific to a model. So another thing to sort of consider is that this is just to reinforce that a human word is not an LLM's token. So I have this suffix ER, and you can see I'm assigning a different token as an example. Another thing to think about from a tokenization perspective, when people develop these models at scale, essentially they would have trained across a very large disparate data set. And the optimization game you have to think in your head is, okay, what series of base tokens can help me to recreate this entire data set that I've seen? What's the most efficient proven vocabulary that can recreate that? So as you think across LLMs, across different domains, and you have different types of vocabulary, different terms, that problem becomes more complex. So for instance, I believe Llama 3 has 128,000 tokens in its vocabulary. So that's just a proxy for you to understand. And a lot of times, tokenization is done on the CPU because it can happen quite fast and it's not computationally heavy. But we'll talk a bit more about that. So each of those tokens inside of your LLM, there's some embedding table. So I go to look up the corresponding embeddings. This is what the actual model is going to work on. It's not going to work on a sequence of token IDs. This is just for you to essentially do a lookup. And from that, once I have these embeddings, this is what your actual prompt looks like. So when I say make me sound smart, I'm just truncating to that. When I do tokenization, I get this corresponding matrix. So in this case, you get the same corresponding matrix with an extra, embedding. So as you think about what you're doing on the GPU every time you talk to one of these models or you interact with it, you're essentially putting a big matrix on the GPU. So just to reinforce that point, the larger the prompt that you have, essentially the larger the matrix on the GPU, which means when you think of a GPU and what's happening from an LLM inference perspective, you're only going to have the model itself, and the remaining space that you have is meant for all of the tokens across all of the requests. So the more requests that you have, you essentially get less space for each request on the GPU. So you have a fixed amount of memory with which to process and to serve all your customers. So now we're going to talk about this thing called KV cache. You'll see KV cache mentioned in documentation. Lots of different types of optimizations go into making LLM inference very efficient, and think of that as memory. An intuitive thing for the attention mechanism is just allowing the model to focus on important tokens. So the question that you should have in your mind when I'm going to generate the next token, or in this case on your side, what were the most important tokens that I've already seen that help me to generate the next best token? And think of it, when you're talking, like I said, I'm keeping track of everything that I said before, and the next word that I generate is a natural step to what I said before. So once again, we're going to go at a high level. So I'm saying make me sound smart, and I'm going to generate this token LLM, and I'll show you sort of the value of the KV cache once you come back on the other side. So I'm replicating this matrix representation that I showed you before of that particular prompt. I'm just repeating it here. You don't have 3 copies of it on the GPU. And when you think about what are model weights, there's just a series of matrices and a bunch of different layers, right? So it'll go sort of in sequential order in terms of processing. But the 3 main matrices, which are collectively known as an attention head, there's actually one more matrix, it's not shown here, would be your query key and value weight matrices. And when you do this matrix multiplication, this is the first step before you go to sort of a final attention mechanism. I don't show the math of attention mechanism here. Feel free to check out many different great tutorials on that online, but I really want you to understand the value of the KV cache. So once I do this matrix multiplication, I get the corresponding key and value matrices. So notice one thing. So I had 4 vectors coming in for my prompt for 4 different tokens or words, not necessarily words. Once I go through that matrix multiplication, now I have 2 of them, right? Even though the size of this embedding is typically different to the size of that embedding, depending on what your weight matrix looks like. Now I'm essentially duplicating it twice, and that's going to help me to process the remaining tokens coming afterwards. So who cares about the KV cache? Why are we doing this? So now I generated the token LLM on the previous slide. So what I'm showing here is I looked up the corresponding embedding for that token LLM. In this case, we're just saying the LLM is just a single token on its own. But notice I'm not passing in the data that I had before. So I take the same model weight. So this is the next iteration of your generate. Now I'm in generation. So before I was in pre-fill, I got my KV cache, and now I'm in generation. So I'm just going to generate tokens. And this is happening across all the requests, all of the users. So think about these large LLM system providers, how many users they have hitting the system. And there's only sort of like one loop that's happening. So once I do this, I get this corresponding embedding. So instead of passing in all of the data that I had before, I actually just maintain the cache that I'm storing on the GPU, and then I send that off to finish the attention mechanism and then to choose the next best token. And you just keep repeating that in in blazingly fast loops. And so there's typically one engine that's going to process all the requests coming in. And as I said before, that engine can either be doing attention on like a big block when you first come in, or it could be just generating tokens for everyone else. So hopefully that makes intuitive sense. When you think of a model, Llama has 32 attention heads. This is kind of what's happening under the hood. So you have 32 essentially of these big matrix multiplications happening almost simultaneously or blazingly fast. And this gets more complicated when you do things like tensor parallelism, which will help you to split models across multiple GPUs. And the goal there is for you to actually get to increase your latency. Here's a good proxy for you to keep in mind. Remember, it's how much GPU memory do I have? How much does my model pick up? The remaining is left for all of the requests. So if you take the number of parameters, multiply it by 2, that gives you your FP16 memory. So you can subtract that from your total GPU memory across all your GPUs typically. And that gives you how much space you have for KV cache. In addition, if you use FP8, this is why people like the Hopper GPUs and the Ada Lovelace GPUs. They give you that ability to do FP8, which is half of FP16. So now a Llama 3 8B will be 8 gigabytes of memory. In addition, the math happens almost twice as fast, so you get this corresponding speed up. So a lot of the results that we put out at NVIDIA are FP8 enabled, and that's why you see people just really rushing towards those GPUs. This is a fantastic blog for you to keep track of, so just search up Mastering LLM Techniques. There's some really cool equations in there for you to estimate what is the KV cache size, meaning what is the total number of tokens that I can process in the memory that I have. And the other thing I encourage you to remember is that when someone says my context length, that means both all of the tokens of my input and my output, because every single generation loop, I have to think about what did I say before and what am I going to say next. Okay, so now that we talked through some theory, hopefully you have a better intuition as to what's happening when you call any of these LLMs. And we're going to talk about the LLM, retriever, and re-ranker NIMs. So NIM stands for NVIDIA Inference Microservice. So it's our way of packaging and optimizing these models so you don't have to do a lot of that hard work. So NIM specifically, as you think about it, so we have some standard APIs. Think of it as just a container that you pull an optimized model. You don't necessarily pull a base model and then have to optimize it. It's already optimized and ready to go. Under the hood, in some cases, we have Triton Inference Server. So if you've not checked out the open source project Triton, you can deploy computer vision, PyTorch, TensorFlow, Python models, any different types of models. That's what we use to deploy all models here at NVIDIA. You have things like GPU operator, which will detect how GPUs are installed on your system across nodes. And you get a bunch of different metrics as well. You can scale this on Kubernetes. You're going to see that today. And under the hood, we have TRT-LLM. TRT-LLM is NVIDIA's model compilation package. So if you want sort of the fastest way to run LLM models on NVIDIA GPUs, use TRT-LLM. If you want the fastest way to run deep learning models on NVIDIA GPUs, make sure to use TensorRT. You can actually save a lot of money. And in addition, we have stuff for p-tuning and LoRa deployments as well. So what's going to happen when you pull a NIM container? So you'll do this Docker run command. We'll pull that image from NGC. Remember, we're pulling a sort of optimized model. I'm going to detect the hardware that you have. Once I've figured out what hardware that you have, I'm going to create these caches so that I can store those optimized versions of the model so we can get it loaded quickly. And then we're going to try to download the optimized model from NGC. That's just our online repository. If there's a TRT-LLM engine, we'll pull that engine for that model based on the GPUs that you have. If not, we'll default back to Hugging Face and VLLM. So you always have sort of that completion across many different models. So we give you that optimized version depending on where you are. In terms of architecture, what's happening under the hood is that we're going to go from the top. You have an OpenAI compliant API. So as you think about LLM routers, not everyone is going to use a single model. You'll use a variety of different models and route to them for different use cases or different types of queries. And that's built on Fast API. So you have either a completions endpoint, a chat completions endpoint. You can query what models you have, check for health status, and there's a bunch of different metrics that you get through Prometheus as well. And in the LLM executor, depending on which model that we're running, we can interpret TRT LLM models and the LLM models as well, or the LLM engines specifically. As you think about what does NIM mean, it's not just LLMs. Every single domain NVIDIA sort of exists across all of those. So this is the deployment path for NVIDIA if you want to consume any of these models across the different domains. So keep an eye out for that, especially as multimodal becomes a lot more popular. And a lot of these models are directly focused on solving a domain-specific problem, let's say in healthcare, in retail, et cetera, et cetera. When it comes to LoRa deployment, so we have that capability, and this is just a simple example of saying, okay, I have a set of requests coming in. I have 3 different use cases for those requests. Why do people like LoRa's? I have a single base model, and then I have corresponding adapters for different use cases. That helps me to save on my overall GPU deployment. Under the hood, we'll have this thing called an adapter store. So we'll store all of the different LoRa's that you have to go to deploy. And then there's an adapter cache that helps you to get these things loaded into memory very quickly. So we'll load it in CPU memory and get it ready to be loaded into GPU memory, depending on how you're swapping them in and out. These next 2 examples is just about what's actually happening when you use a NIM and what's happening with optimized engines. So these are things that you'll see online. So depending on the GPU that you're using and the corresponding number of GPUs that you launch, we have 2 different types of models. We have a throughput optimized model and a latency optimized model. So throughput latency just typically means you have a higher tensor parallelism, means you split it up across multiple GPUs. That helps you to run 2 parts of the model at the same time. And you see on the right-hand side, we get very specific. So I'm saying in this case, I have an H100 an FP8 engine, FP8 throughput engine versus a H100 latency FP8 engine. And you can see typically the latency engines will have an extra GPU attached to them. So that's how you end up getting sort of fast deployments. And we have different versions for LoRa's, et cetera, specific to that GPU. That's how you end up getting the speed. Here's the same thing for Llama 3 70B as an example. Notice that the number of GPUs are a lot more because you have to do 70 times 2 equals 140. That's just the memory for your model in FP16. And then you need some more memory for the actual tokens themselves. So that's kind of how it works at a high level. And when it comes to the retriever and the microservice, the retriever microservice, so that is composed of the retriever embedding NIM. So we have some very accurate embedding models. We've won some very popular benchmarks. And then we have a re-ranking NIM as well. So the retriever microservice will encapsulate all of these. If you do have vector databases, we accelerate many different types of vector databases on GPU. You can get insanely high recall and very fast indexing speeds as well. So something to consider. In terms of the embedding and re-ranking NIMs, here are 4 of them that you can sort of download and try out today. So we have some Mistral versions of it as well. And then the re-ranking NIM is a Mistral base. So you can see that how LLMs, these newer age LLMs are being used for both the embedding and re-ranking stage. It's not, let's say we were using BERT, et cetera, or some XGBoost model to re-rank. So you're seeing that penetration of these new models. And I'll sort of conclude here when it comes to sort of accuracy. So this is an example with Cadence. Top 1 just means your first result. Top 10 just means your top 10 results. And as you can see, when you start layering both retrieving and re-ranking, you get a corresponding increase in overall accuracy. So I'll stop sharing and I'll hand off to Anna, I think.
All right, thank you very much, Mark. And let me see if I can share my screen. I'll probably ask you to tell me if it looks okay. Yeah, all right. With that, I'm going to start discussing how we use NVIDIA NIMs to create RAG applications. Just a quick PSA. If you do have any questions that you'd like answered, please drop them in the Q&A box because we'll probably miss a lot of the ones that come in through regular chat. I've already noticed a few that I've taken note of, but please do try to use the Q&A functionality. All right. I think a lot of you are probably already quite aware of what RAG is, but I've decided to do a very quick intro into the concept of RAG. So I'll start with that, and then we'll start looking into how you can use Nvidia NIMs within those RAG pipelines. So the idea of RAG is usually as following. Imagine we have a database somewhere that's storing our documents, and that can be any one of these vector databases that you see here. At least this is how it works in Haystack. And we usually also have an instruction that we call a prompt. And in most use cases, we see people talk about RAG in the context of question answering, where that instruction might look like what you're seeing here, given the documents, answer the question, and then we have some documents that come in and a question. And the way it works is we first have a question and we retrieve the most relevant piece of context or the snippet of context from our database. And we quite literally add that to the instruction, to the prompt, and we send this whole thing, this whole instruction with the augmented context to a large language model. Again, this really depends on how you structure that prompt. This isn't necessarily always question answering. RAG is definitely used for summarization, question generation, a whole load of other use cases as well. For this webinar, we're going to be doing the most classic one again, and we're going to be looking at question answering. So what we're going to be building, our RAG, is going to be based off of a PDF. You'll have that PDF in the repository we already shared. And it's a PDF, which is a research paper on ChipNeMo. And we want to be able to do some sort of question answering on this PDF. And we're going to be storing it in, for this use case, a Quadrant document store. Quadrant is a performant vector database, and you'll see how we add this document to a Quadrant document store alongside its embeddings. So usually, to be able to create a RAG pipeline, there's often a pipeline that's very much overlooked. And we call this the indexing pipeline, where you have a bunch of documents and potentially you want to clean them, split them, and then you also want to create embedding representations of these little snippets of context. And finally, you want to store them somewhere. In our use case, this pipeline is going to look like the following. We have our original PDF. We're going to convert that into a structure that Haystack can understand. Then we're going to clean it up. We're going to split it into smaller chunks. It is 17 pages of a PDF file, I think, as far as I remember. And then we're going to be using Nvidia NIMs as our embedding module. Specifically, we're using the Snowflake Arctic Embed L model here. And then we're going to be indexing that into a Quadrant document store. So once we have that, we have context that we can use alongside an embedding model. So a user can ask a query, and in an ideal world, Quadrant is able to return the most relevant top 3, 5, 10 snippets from our whole PDF to answer the question. Then we start building the most popular pipeline, which is the RAG pipeline. And RAG consists of two major steps, retrieval and generation. But actually, within retrieval and the generation steps, there's quite a few things that are going on. First, we have the user query. And remember that we have by now indexed our documents and have embedding representations of those documents in our Quadrant document store. We need to embed our query with the same model so as to be able to compare our query to all of the existing documents in our document store. So we first embed the query, then we retrieve documents, and then we build a prompt. In Haystack, we have a component literally called the prompt builder for this. And that prompt is now expecting documents and potentially a query as well. And then finally, we generate a response. Again, for our use case, what we're going to be doing here is we're going to be using the same embedding model that we had, Snowflake Arctic Embed L. And then we're going to also have a generative model. And here we're going to be using a Llama model. All right, so where can you find these models? Anshul is going to talk about how you can host your own NVIDIA NIMs. What I'm going to be using and what you can already get started with, it's very easy to get started with, are the hosted NVIDIA NIMs. So this is where you can find them, build.nvidia.com. And you have a suite of models that NVIDIA is providing you off the bat, and you can simply generate yourself an API key. And all of the code I'm showing you from this point onwards, you can use if you have an NVIDIA API key through this UI. We'll also share a link to that in the chat as well. So first off, for anyone who isn't familiar with Haystack, Haystack is a fully open source AI framework. You can pip install Haystack AI, and you'll have all of the components and functionality that you need to create these types of pipelines. And Haystack is built on the idea of creating pipelines sort of like a graph. You create components and you connect those components in a logical way, depending on what you're trying to build. I haven't gone through the indexing pipeline here. I'd like to focus on the RAG pipeline, so let's take a look at that. First, we're going to be starting with the embedder. So as you can see here, we have the NVIDIA text embedder. This is going to be the component that is able to embed the incoming user query. Then we're going to have a retriever. We're using Quadrant, so we have the Quadrant embedding retriever. And then finally, we have the prompt. And I want to point out a few things here. As you can see here, the prompt has question, and there are curly brackets, and it has query in there. And then it also has context, and then there's a for loop. In Haystack, we use Ginger templating, which is pretty useful because it means that we can have these types of for loops and loop through documents and be very specific. As you can see here, we're embedding specifically document.content. And then finally, we also have the NVIDIA generator, and this is where we use the Llama 3 model. You can also decide how many tokens you want it to generate and so on as well. So we have these components ready. Again, in the Haystack universe, the way you create these types of applications is by creating pipelines. So you start by defining a pipeline. I've called it RAG. And then you simply add components. So here I've given names to my components. They're not very creative names. I have the embedder, the retriever, the prompt, and the generator. And then the final thing I do, I connect these components. And this is where you can get very, very specific with Haystack, and Haystack pipelines, because of this feature, can also branch out and loop, etc. as well. Those are pretty advanced pipelines. But this is a one-pass pipeline where we're asking the embeddings created by the embedder to be inputted to the retriever query embeddings. And very specifically, we're asking for the documents returned by the retriever to be added to prompt documents. And if you remember, we have documents as input to this prompt here. The final thing that we did for this demo, Anshul and Miriam helped me build this demo, is we deployed it. We deployed it with a tool that DeepSet also provides alongside Haystack. It's just one of those options that you have to deploy these types of pipelines. Hayhooks can deploy pipelines that have YAML definitions, and all Haystack pipelines can be converted to YAML simply by saying pipeline.dump and then dumping it out into a file. So already in the repository we're sharing, you'll have the YAML definition of the pipeline that you'll see running right now. And we've exported it to a file called rag.yaml. Once we have that, we can deploy the pipeline. So Hayhooks deploy rag YAML, and then you'll be able to interact with your pipeline. So with that, hopefully you can see my editor. Can someone tell me if this is large enough or if I should make it a bit bigger? Is it okay?
Yeah, I think it's okay.
That looks okay.
Yeah.
All right. So the way we deploy this is we Docker compose up initially. I've already done that, so I'm not going to do it again. Hopefully it's still running. And then finally, we say, Hayhooks deploy rag.yaml. And I can run this, but it'll tell me there's something already running because I have it running anyway. And you can see here the same exact code that we had a look at earlier. We have our document store. We have our embedder, which is the NVIDIA text embedder. We have our retriever. We have our prompt that we can change around if we want to, and so on. And finally, we have our RAG pipeline. And if you do want to run this script as is, this will dump out the RAG pipeline as a YAML definition by default. So once we have this running, hopefully I can head back and leave this and see what we have here. You can go to localhost 1416 docs, and you'll start being able to play around with the pipelines you have. So we've deployed the RAG pipeline, so you'll be able to see that we have this RAG here. And hopefully, wish me luck, we can try it out. And as you remember, we had a PDF file all about ChipNemo. So maybe we can start by asking, what is ChipNemo? And we need to provide this query both to the embedder, because we need to embed this query, and to the prompt. If you remember, the prompt builder had query in the prompt text. And we execute, and it looks like it's running, and we have a response. And here we are. So you can start playing around with this, and you can also have this just running as a service and query it from any other application that you want. The other thing you can do, which is a very useful, functionality, which I'll also see how else you can play around with this, is you can visualize your pipeline. And here you are able to then see what the pipeline structure actually looks like and whether it's what you expect. Finally, another thing I want to point out is what happened to our documents. So initially, we knew that we had to create an indexing pipeline, which again is available in the repository we're going to share. As you can see, we've got the PDF to document converter, the cleaner, the splitter, and we've split by 100 words. So where did this all go? You can also go ahead and inspect that. As you can see, we have all of those snippets of our documents alongside the embeddings in our Quadrant document store. The last thing I want to share about how you can create these pipelines is actually something very new. And if you like, you can join the waitlist already. And you can completely visually create this. So you saw just now how you could create a visualization based off of your Python code. But another option you have at hand within a month's time is going to be creating them completely visually. So as you can see here, we have our embedder. You can define what kind of model you want to use, connect that to the Quadrant embedding retriever, and then finally go all the way into configuring your prompt, giving it the prompt that you want to execute your pipeline with, and so on. And the really nice thing here is I mentioned to you that we can use YAML definitions to deploy Haystack pipelines with Hayhooks. Again, this is just an option. This is not a requirement. You can also create your own fast API definitions and so on. But you can get the pipeline definition in YAML within the Pipeline Studio. So this is a new product that we have called DeepSet Studio. If you do want to, you can sign up for the waitlist. And once you have that, you can go ahead and deploy your RAG pipeline. All of this is available in our open repository, which we've shared. We'll share it again. And you have all of the instructions on how to run these. Now, so far, I have discussed how you can create these pipelines completely with Nvidia NIMs that are hosted by Nvidia. But there's also an option to host these models completely yourself. So for that, I'm going to hand over to Anshul, and I'll ask you to share your screen and take it from there.
Yeah, thank you for giving the intro. Let's see if I can share my screen. Do you guys see my screen?
We can see.
Yeah,
we do.
So I'll cover the part of deploying and scaling LLMs on a Kubernetes cluster with Nvidia NIMs and Haystack. And assuming this Kubernetes cluster can be anywhere. It could be a CSP provider Kubernetes, or it could be your on-prem Kubernetes cluster. So now let's see. So I'm deploying on the on-premise Kubernetes cluster, partly with the CSP. So yeah, it's a mixed actually. So let's start. So over here, as you saw, Tuana showed you the RAG pipeline in a high-level way. So now you need to know that on a Kubernetes cluster, it requires a lot of components to make it work. For example, on the left side, you can see I have a Kubernetes cluster, which is running on a host, and that host has some GPUs, like 8 GPUs over here with DGX H100. On that host, the Kubernetes cluster is deployed. Within the Kubernetes cluster, I have a GPU operator installed. And this GPU operator is you can download or install it via the Helm chart. And along with that, I have a Prometheus Grafana stack for monitoring my Kubernetes and all, as well as the NIMs or my whole rack pipeline. So that's like the basic. Now, which comes with the NIMs and the rack pipeline are in these three blocks, which you can see over here. The blue one shows the LLM NIM. The orangish or reddish one shows the NIM embedding, and the last, the yellowish one, is the vector database. Within the blue, you can see I have a deployment of the Kubernetes. Within the deployment, I have the LLM NIM pods, which you can scale using the HPA. And underneath, they are using the PVC with the storage class for storing the model. And you can expose these deployment via Kubernetes service like cluster IP, node port, or a load balancer. The same is with the NIM embedding, where you have a deployment which contains the HPA, and the NEMO retriever text embedding NIM, which you can also scale via HPA. Again, the PVC and storage class for saving the model itself. Lastly, we have a vector database. So vector database could be any vector database, like Tuana mentioned about Qtrend. So we'll use Qtrend as part of this demo. And then you can have an ingress rule to expose these towards the outside environment as you want. So let's start with the blue box. So as part of the blue box, so we'll use the LLM NIM Helm chart, which is available on the GitHub. So if you go to our Git repo of the Nvidia NIM deploy, so you would see over there the Helm chart, which contains the LLM NIM Helm chart, which we are using as part of this demo. So apart from the Helm chart, we need a NGC CLI API key where the NIM container and as well as the model reside. And this is so like, for example, which Mark also mentioned, that you can pull the container from the NGC. So it's like NVIDIA GPU Cloud. And here you can have a container, Helm charts, and the models, which we are using as part of the demo. So I'm using a namespace webinar as part of this deployment. And you can see within my Kubernetes cluster, I have 3 GPU nodes and 1 CPU node. And this GPU node is an A100 GPU node with 8 GPUs and 96 CPUs. So all of these GPUs are the same. And I'm setting my current Kubernetes configuration or context as the current namespace, which is the webinar itself. The first thing which I will do is I will pull the Git or clone the Git repo. And that Git repo contains the Helm chart. And to deploy the Helm chart, I need to have certain secrets as part of the Kubernetes cluster. One of the secret is to pull the container, which is like I'm putting the name over here, NVCR image pull secret. The another secret is required to pull the model, which is the NGC CLI API key. So once you have these two secrets, your basic things are done for deploying the LLM NIM. Now, the next thing which you need to do is have a custom Helm chart values over here. So for example, I'm setting my repository as Llama 3.18 billion instruct. So I wanna use Llama 3.18 billion instruct model. You can, the secret which we created above over here, you can see the model name is mapped to the container itself. And yeah, and lastly, the persistent storage. So like, so you can have a different storage based on how you have deployed the Kubernetes. Like for me, I'm using a local path-based storage class, which underneath is using cluster file system. And yeah, and then you can specify how many GPUs you wanna give it to the model itself. So once you have these custom NIM LLM values, Helm values file, then you can deploy using the Helm command. Helm install, specify the release name of the Helm, the custom values file, and the chart itself, which we downloaded from the Git. And once you do this, so then you would see NIM LLM pod would be started to run. The first thing it will do is it will download the container from the NGC. And then once it downloads the container, then it will try to download the model itself. And let's see what that information looks like. So this is over here in the logs. So you can see it downloaded the container. And after the container downloaded, it starts printing certain logs. And within the logs, you can see that it detected two compatible profile based on my current GPU, which I'm deploying it on. And one of that profile is the TensorRT LLM A100 BF16 TP1 throughput, which Mark explains about these numbers or these values. And another one is the VLLM FP16 TP1. And based on the GPU optimized profile, based on the GPU, the particular optimized profile would be chosen for the deployment. So as for here, you can see my GPU is A100. So it shows the TensorRT LLM A100 BF16 TP1 throughput profile. So once it is done, so you have your container up and running. So you would get the Kubernetes service to access it. And the first thing you can do is check this is the Kubernetes internal endpoint, how you can access the service, like the service name, the namespace name, and service.cluster.local. And view on models endpoint, then you can see the model which is deployed currently as part of the LLM name, which is Llama 3.18b instruct. And now you can run the chat completions endpoint and say, ask, what shall I do in a Munich for a day? And this, you can send it to the LLM, this chat completions endpoint. You can change the content or the prompt itself, however you want. And for example, I got traditional beer, Bavarian beer garden. Yeah, so that's a LLM name is up and running actually for me. And lastly, I want to show as part of the LLM name is that you can have a different metrics, which Mark explained that you can get from the LLM name itself, like the time to first token, seconds count, yeah, many more. That's the LLM name. So now for the retriever text embedding name, it's a very similar process. Get the Helm chart. And this time the Helm chart is on the NGC itself, not on the Git as for now, but it's public, so you can download it. Once you have the Helm chart, create a custom embedding name values file. So like I'm over here using NV embed QA E5 V5 model. And you can specify the persistent storage which you want to use. And if you want to limit to a certain resources in the Kubernetes. Once you have that, then you can run again the Helm install command for the embedding itself. And then you would have your embedding model as well as up and running. So you can query the endpoint, the v1/models for the embedding as well. And you would get the NV embed E5 V5. And you can, if you want to check if the model is correctly deployed, so you can send a prompt to the V1 embeddings endpoint and asking to create an embeddings of the hello world, like a phrase input. And then in the end, you would see these embeddings shown up. Similarly, you can get its matrix as well, and that's the matrix endpoint. So now you have both the LLM name and the embedding name up and running. Now, the third thing which we want to do as part of the RAG pipeline, we want to also monitor both the names. As part of the monitoring, my cluster already has the Prometheus deployed, and Prometheus and Grafana. So I'm just extending those Prometheus and Grafana to monitor my additional containers or additional pods, which are then name pods. And for that, you can deploy the Prometheus service monitor, which pulls the metrics from a certain endpoint, like the metrics endpoint within a NIM LLM, and saves it into the Prometheus. Then from the Grafana, you can visualize the NIM LLM NIM metrics, and the same for the embedding NIM metrics. And once you run this, so in the Prometheus UI, you would see these service monitor up and running. So that shows you that these are now monitoring these endpoints, and Prometheus is collecting all the data for you. So now I have the LLM name, I have the embedding name, I have the monitoring also set up. The third thing which is missing is the deployment of the vector database. As Tuana showed in her presentation, we use Qdrant. So I deployed the Qdrant over here, the same process using the Helm chart, get the repo, install the Qdrant, and then you would have the Qdrant up and running as well. So now both the names plus the vector database, we have all the components we need for our RAG pipeline. And that for the RAG pipeline, we are using Haystack over here. So which Tuana showed you the endpoints, which she showed her in the presentation were the API catalog endpoints. So now instead of those endpoints, we will use our self-hosted NIM endpoints. So like over here for LLM NIM, for the embedding name and the quadrant. So now all the components of your rack pipeline are deployed within your Kubernetes cluster, so you don't have to go outside. And the same thing, I'm doing it calculating the embeddings from the data chip Nemo paper. So I'll not go into the details of this because Tuana covered it. I just showed you that you can easily replace these endpoints with the internal one and it will work as it is. So it's exactly the same, like calculate the indexing of your documents. So like, for example, created the pipeline over here. And then if I run this indexing, so it will calculate all the embeddings from that document. And then you can go to your Qdrant database to check to check the embeddings actually if you want to. So you can, as you can see over here, the content is over there. So yeah, and then you can have your rack pipeline, which uses the internally deployed embedder plus the LLM name. And then you can, once you have that pipeline up and running, then you can do the prompt as Tuana did in her, the Hey Hook, the UI, which he showed in the presentation. So like I'm asking over here, summarize the chip Nemo paper. So it's a very, like it's asking the same question on the chip Nemo paper, and then you can see the chip Nemo paper summarization. And once you have this, you can also dump this rack.yaml and then deploy it anywhere else as well. So now we have the names, all the names plus the vector database, the rack pipeline. The last piece, which I want to show you, is how you can auto scale these names, which are deployed on your Kubernetes cluster. So as part of the auto scaling, so within the Kubernetes, you have an HPA, which is a horizontal pod autoscaler, which scales the pod depending on the certain metric. And by default, you only have CPU and memory metric by which you can scale. For adding an extra custom metric, you can deploy a Prometheus adapter, which will then query those metrics from the Prometheus and register it as part of the custom metrics API of the Kubernetes. And once you have it, then you can ask the HPA, horizontal pod autoscaler, to use that custom metric to scale the NIMs. For example, I created a custom metric, which is called as the NIM LLM GPU average, which is calculating the average GPU utilization of the NIM LLM, and the same with the NEMO embedding as well. So that's my two custom metric. And once you have this custom metric, then you can use in your horizontal pod autoscaler these custom metric to say that I want to use this metric. And if the value goes above 30%, average value goes over 30%, I want to scale between 1 and 2. Or at the moment, I changed it to 1 and 5 actually as well, that your min and max replicas. Similarly for the embedding name. And once you have that deployed, so then you can test those, like the scaling is working or not. So I use for testing for my deployment, just a minute. So Locust. So Locust is a nice tool if you want to do a testing, and you can see I'm sending the prompt value, which I showed you before, to this endpoint, which is a LLM NIM endpoint. And currently I'm sending it like replicating 20 users as part of the like a load testing. And you can increase it depending on how you want. So over here, you can see I did some testing with varied amount of number of users. And now if you see based on this, how does my NIM behaved? And that's over here in the Prometheus dashboard. You can see the scaling of the LLM NIM. So this shows you the GPU utilization, the stacked chart of the GPU utilization by each NIM over a period of time when I was sending the load. And you can see it scaled to 6 over here, the 6 because one was before, and now it's, if I change it to, you can adjust the timing actually depending on how you want it to be. And last one dashboard, which I want to show you, that the metrics, which Mark was mentioning that you can have within the name, and which I showed you before, we have a Grafana dashboard as well for that you can see like time to first token, the KV cache utilization, requests per second, how many are waiting currently, how many are currently running. So all these values which you can monitor and see how the utilization of the names is. Yeah, so that's how you can deploy the LLM name, the embedding name, and form a rack pipeline on your own Kubernetes cluster. Yeah, Tuana.
All right, thank you very much. And let's make it official. We can start the Q&A. We have some resources here that you can scan the QR codes if you like, but we'll also share this in the video description. We have the documentation here, the example repository. All of the code is in the example repository, not only for hosted NIMs, but the notebook that walks you through deploying NIMs are also in there. All right, we tried to answer some questions along the way. Thank you very much to Vladimir and Anshul and Mark for helping answer these questions. And I'm going to try walk through some. I think there are quite a few to the NVIDIA folks. So yeah, let's give it a start and we'll try to get through all of them. I think we'll go a bit over time, but that's okay. What is the benefit of running the LoRa optimized engine versus the latency or throughput engines?
Yeah, you don't want to necessarily think about it as LoRa versus latency versus throughput optimized. Just think of, okay, I'm deploying a LoRa. That's the most optimized LoRa deployment that you can have. The latency and throughput optimized engines are not necessarily if you have a LoRa. So those are optimized engines for those two use cases. So think of them sort of separately, not necessarily versus.
There were also quite a few questions about licensing and running NIMs 100% locally. So maybe you can expand a bit more on that. I'll just pose the question as it is. Is it possible to use NIMs without a commercial license? Also, is it possible to run NIMs 100% locally without internet access?
So technically, AirGap support, I forget where we are on that right now. Even though we do make a call back out to NGC,
No,
you can run.
Yeah, you can actually
correct.
run now with the newer release completely 100% on your environment without going anything to the internet. So fully on-prem.
And yeah, correct me if I'm wrong, Anshul, we have 90-day license for NIM, correct?
Yeah, 90-day license, so that requires, so we also have a free developer program if you are a student or like part of the university, so you can get these names for free.
I think this following question is kind of related, and I'm also curious myself. If I create my own fine-tuned model, what's the process for creating a NIM for it?
Yeah, Mark,
I don't think we have. Yeah, I think fine-tuning support is coming out, not probably the next release or the release after. So, but in general, what you'll have to do is either compile, depending on what your base model is. So if it's one of the standard models, so if you go to TRT-LLM GitHub, you'll see all of the different types of models that are optimized. So you'll end up having to build your own engine under the hood. That software will help you to build that engine depending on the type of GPU that you're using. Always remember, you build an engine specific to the GPU and specific to the number of GPUs. So if you build, let's say, Llama 3 70B, and you build that to 2 H100s, that's a different engine if you build it to 4 H100s versus 8, or 2 L4s versus 4. So that's one thing to keep in mind as well. So maybe in the next couple of releases, you'll have your own fine-tuned model support.
Again, I think this is similar, but maybe there is a slightly different answer to it. It's the last question we got in the Q&A. Can you run quantized models in NIMs? If yes, what format is required?
The models in NIM are technically quantized already to a degree, depending on the type of GPU that you're running. If you want to do it from scratch, you'll have to deploy a TRT LLM. You'll have to build your own engine again. And NIM should be able to pick up that particular engine and run it.
And I think finally for NIMs specifically, there were some questions about computer vision models. I think we can also share maybe if someone can drop the documentation on how to use computer vision models, that would be great. But what's available? How can we use them? How do you see people using them?
So right now, the best place to see what's available from a NIM perspective is build.nvidia.com. That's sort of the latest. And we work with all of the different AI startups behind the scenes. So the day that they launch, it'll be available on build.nvidia.com. And so the vision language model specifically, separating that from traditional computer vision, a lot of folks are using that for just video analysis. For instance, in retail, people are trying to see, okay, what are people doing? Activity recognition, things like that. In some cases, you're seeing folks counting. So many different applications. And we have a visual agents. I'll see if we find the link, a visual agents early access program coming out now. So you can deploy a lot of these vision language models quite easily. I think we're building the whole fine tuning and not necessarily LoRa, but adaptive capabilities to do that quite easily. So that's coming.
Another question that came through was about memory management. So I'm going to read it out loud. I'd like to understand how to manage the memory requirements for handling the number of requests to my application, as well as how to scale in response to the request volume. And I'm going to assume this is based on requests to the model. So maybe you can expand on that too.
So it depends. So it depends like how the prompt is and how big the prompt and what is that asking. So depending on that, so you can do some testing around, like I did some with the locust. So you can do some testing that how much your memory is utilized based on that. And then you can add that metric into your auto scaling capability. And based on that, you can scale the NIM. And like we showed, there are a bunch of metrics from the exposed from the NIM. So you can see which metric might be even better than just the normal memory utilization.
Nice. All right. Thank you very much. I think we're a bit over time now, but I'm going to wrap up by answering a few questions that came, which is more about Haystack. I did try to there were some questions that are quite similar to each other. So we did try to sort of group them together. So if you haven't seen your specific question answered, I tried to group them with others. But just a quick information for everyone. We will send out an email with all of the resources as well as having it in the description. And we'll try to share everything, slides and code and documentation, all of that. Hopefully you'll get that tomorrow, latest Friday, you'll have it in your inbox. And then the other thing I wanted to point out is we've had a few questions about the PDF that we were using and the fact that sometimes PDF has different graphs in it, images in it, etc. The PDF converter I used is a very basic one. So it's only looking at the text in the PDF. Yes, there are a lot of use cases where you would want a way more advanced converter. And for this, at least with Haystack right now, we have integrations with a few other providers that completely focus on the pre-processing of complex input documents. For example, unstructured is one of those examples. But we're also working on introducing some of our own. And the similar question came about splitting. Another thing that we showed just for the purpose of this demo, it was a very naive approach. You may have realized that we just simply split the document by 100 words. But you have a lot more flexibility on how you actually do the splitting. It doesn't have to be based on words. It also doesn't have to be a clear cut. So another option you have is defining what the overlap looks like, for example. And we're also about to introduce an experimental component that can also reference the parent document and not just simply be splits of documents. So I hope that clears up some of the other questions we also had. Let me just skim through the remaining questions. I think with the last thing I can ask is maybe about the Dockerized containers. If I run NIMs using Docker, can I also have a dev container with Python, Haystack, etc.? If yes, do I have to run 2 containers simultaneously, one for dev container, one for NIM, any inference?
Yep, I think so you need to be having the 2. Better would be that, because you don't want to mix your the NIM container with the other container. So it's better if you have a dev container, attach it with the other container, and then you can play around with these 2. So it's like a deployment in the Kubernetes world, like combining the 2 containers within a single pod. I hope that answers the question.
All right. Okay, one last one, and then we can wrap it up. It came in through chat, apparently. Is there a way to use Nvidia NIMs for handling a large number of requests, more than 1,000 requests, with a pay-as-you-go option in case we don't have sufficient resources to deploy NIMs on our hosts?
I'm imagining this is about the API catalog names.
Yes, I think so too.
I'm not sure if I can answer that correctly, but it would be better if you send us an email, then we can check it out internally and come back to you with your specific needs on how much you need. And yeah, we can always do something actually.
Yeah, if you plan to deploy NIMs in production, we can work something out.
All right. Thank you very much, Anshul and Mark. Thank you everyone who attended, who sticked around for the whole Q&A session. As mentioned before, we'll do our best to have this session up on YouTube as soon as possible. And we will also send you all of the resources in email. And with that, I think we can say goodbye. And let us know if you like this session, if you'd like to see more of this, what kind of content you'd like to see. Please do let us know. And yeah, see you next time. Thanks, everyone.